Okay, so now we'll look at the sentence piece tokenizer, right? And here, uh, hopefully the idea is to start with a larger vocabulary and then shrink it, right? So let's see what that means. So now, what is the motivation for a sentence piece, right? So a given word can have numerous subwords, right, that we have already seen, and not just that, right? So if you take even the word like hello, right, and I'm going to take this vocabulary, V, which is HELLO, HEELLO, LL, and HELL. Okay. Now, even with this vocabulary, there are multiple ways of segmenting hello, right? Because if I look at this segmentation, this word is there in the vocabulary. Sorry, LL is also there in the vocabulary and O is also there in the vocabulary. So, this is a valid segmentation as per the vocabulary given to me. Yes. Now, not just this, this is also a valid segmentation, right? Because H is there in the vocabulary, EL is there in the vocabulary, LO is there in the vocabulary, right? X3 is also a valid segmentation, and X4 is also a valid segmentation. But of these four, which segmentation would BPE give? Yeah, so it will first have start with this, right? Everything is a single character, right? So it has gone over this and segmented it, right? Then it finds HE. So what will it do? It will merge HE. Okay. Then it finds EL. Can it merge EL now? No, because EL, there is no E now. It is HE, L, L, O. This is what the state is when I am looking at EL. So there is no EL here to merge. Correct? Right? Then it has LO. Is it possible to merge? Yes. So it will merge LO. So your segmentation now becomes HELLO. Okay. Now there is LL. Is it possible to merge these two L's? No. Because this is no longer an L, it has become a new token LO. So you cannot merge it. Right? Okay. By the same logic, you cannot merge these four because the tokens are HE, L and LO. So you cannot merge them. Right? So the tokenization that it will give is this one. Okay. Now, if the merge operations had happened slightly differently, and this is what my vocabulary is. So the vocabulary is the same. It's just that the order is different, right? It's the same tokens in both the sets, right? But the order of the tokens is different. Here now EL comes first and then HE comes. So now what will be the tokenization? X2, right? Because it starts again with individual tokens, okay? So it starts with H, E, L, L, O, then it goes EL. So EL will be merged, so then your tokens become HEL, L, O. But now HE cannot be merged because there is no E. LO will be merged, so HEL, LO. Now LL cannot be merged and HEL can also be not be merged, right? Correct? So this is what your tokenizer will be. This is the same vocabulary, just changing the merge order is giving different segmentations, right? And this just sort of reinforces what we already know, that a given word can have many segmentations, right? And BP is very greedy and deterministic, right? Because it's going over it in a greedy way, and it's not really thinking about what is the best segmentation. It's just saying, okay, if I go in this order, this is what the segmentation is. The same vocabulary could have given you different segmentations. Is there the case that one is better than the other, right? Now, the probabilistic approach is that if you have a subword sequence, right, you have a sequence of subwords. So this is what your subword sequence is. This is H, E, L, L, O, right? So this is what I mean by a subword sequence. And you want a segmentation that maximizes the likelihood of the word X, okay? So what does that mean? Let's see, right? So this is X, this is the word hello that you have observed. There are many subwords possible or many segmentations possible. Of these, which is the one which actually led to X, right? So that's the problem. So you have an observed variable and you have a hidden variable, which is the segmentation, right? Now, in case of sentence piece, you don't need spaces. You can even deal with languages which have just sequence of characters. So it will also work for Japanese and other languages. Okay. So now this is a subword sequence, x1, x2 up to xn. Now I can compute the probability of this subword sequence. How do I compute the probability of this subword sequence? This probability of the sequence is just the product of the probabilities of all the subwords in that sequence, right? And how do I compute the probability of each of these subwords? Just a minute. Oops. Okay, let's look at this example and then go back to the previous slide, right? So x equal to knowing is the word, and these are some candidate segmentations of this word. Okay. Now for any given candidate, you can find the probability. So P of, you're looking at P of x1, the subword sequence being k, now, ing. So this would just be probability of k multiplied by probability of now multiplied by probability of ing. That's a unigram model that you're using. So this would just be this. Okay. The next segmentation was no comma ing, in which case your sequence is no comma ing. Right? So you're talking about the same word x, but different segmentation. Right? So in this case, the probability is 336 by 4096, clearly better than the previous one. Right? So this, if I just had these two candidates, clearly the second sequence is maximizing the probability of the word x. Right? But now I have one more candidate, which is x3 equal to knowing, and that is just 768 by 4096, right. So clearly this knowing is the segmentation which has the highest probability, and this is what we are interested in, of all the segmentations possible, which has the highest probability, right. And the way we are calculating the probability is just the product of the segments in them. Okay. Now if this is understood, now if I go back to the previous slide, so this is what we were trying to say, that you have a subword sequence. Okay. Now for a given word capital X, there are many sequences possible, and you are looking for that sequence which maximizes the probability of X, and the probability of X is just the product of the probabilities of its subsequence, right. And this we can also, instead of this, we can also write it as log. We can take the log, right, and then write it as summation, right. So this should have been the log probabilities. The log is outside. Yeah, is that okay? So we have understood how to compute the probability of a word given a specific segmentation that you have for that word, right. And now we'll see how using this we can do the sentence piece tokenizer. So let's see. So we set the desired vocabulary size. We say that we want a vocabulary size of some 100k or 30k or something, right. Now we construct a very large seed vocabulary using BP or any other algorithm that you want, right. You construct a very large vocabulary, more than what you actually want to construct, right. So this is all the initial tokens that you had in your vocabulary, right. So as I said, we are starting from the large end, and then we are going to throw away stuff, right. So if you want, you can even start with all the unique words in your corpus, but that may be an overkill. So you can just start with something like BP, which gives you 250k, right. Start with BP of 250k, and then you are going to prune it, right. So you have a very large vocabulary now. Now you have the, what we are going to use is the EM algorithm with very simple E and M step. So in the E step, you are going to estimate the probability of every token in the given vocabulary using the frequency counts, right. So now can I estimate the probability of, can I compute the probability of now? It will just be the number of times now has appeared divided by the sum of the number of times all the words have appeared, right, which is just the total number of words in the vocabulary. Is that okay? Fine. So I know what is the probability. So for each of these guys, I can find the probability, and I needed this because my probability of word X is the product of the probabilities of the tokens in it, right. So what I have now computed is the probability of these tokens. Okay. Now in the M step, for every word in my corpus, right. So now my corpus was, suppose here was one sequence in my corpus, I know something, right. So now for every word, let's take something, I am going to compute what is the best segmentation for something. How do I compute the best segmentation? I can just enumerate all the segmentations possible for something, right? So the simplest segmentation is S, O, M, E and each character, right? Then this something as a whole word is another segmentation, provided something is in the vocabulary, right? Then some comma thing is another possible segmentation. For each of these segmentations, can I compute the probability of that sequence? Yes, I can just multiply the probabilities of each of the subwords in that sequence, right? And then I'll take the one which is maximum, and that is what my best segmentation is. Okay, what's the catch here? What's the problem? No, the problem is that enumerating all these possible segmentations is computationally expensive, right? Because you could potentially have, if something has a length of 8, there are 2 raised to 8 segmentations possible. We are only taking from the vocabulary, but even then there are many segmentations possible, right? So it's like the upper limit is 2 raised to k, where k is the number of characters in the word, but there are many segmentations. You may not have 2 raised to k, that's the worst case, but you may still have many segmentations. And enumerating all of them may be difficult. So we'll need some sort of a fast way of computing that, and that's where the Viterbi algorithm comes in, which is a dynamic programming algorithm, right? So we'll see what we do in the Viterbi algorithm as an example on the next slide, right? But conceptually you understand that I just list down all the segmentations, compute the probability for each segmentation and take the one which has the highest probability, right? Okay. So now I have, since I'm going to retain the best segmentation, so now suppose for something the segmentation received was, the best segmentation was this, and for every sort of word in the corpus I have retained the best segmentation, resulting in some tokens, right? So now I look at all the unique tokens in the corpus again, right? And I'm going to, which is going to be the same as this set, right? Because this is a set using which I had tokenized it. But what has changed is that now some words have got tokenized differently based on whatever was giving the maximum probability for that tokenization or that segmentation, right? So now using that, for every token I'm going to again compute the probabilities. Is that okay? Right? And then I'm going to throw away the bottom 25% tokens or bottom X% tokens which have the smallest probability. Is that okay? And then I'm going to just repeat this algorithm again. So that's all that is there. So you're going to shrink the vocabulary by removing the k% of tokens which had the smallest likelihood, and then you're going to repeat these steps. So you started with this initial set of vocabulary. This gives you multiple ways of segmenting every word. For every segment you chose, every word you chose the best segmentation, right? Now what does that change? That changes the frequency of certain tokens, because instead of using sum, if you have tokenized it as SO and ME, then the frequency of SO and ME will change. That's why your probability for all the tokens will change again, right? So after the optimal segmentation, you're going to recompute the probability of all the tokens, and now the probability of some tokens has changed, right? So now you'll throw away the tokens which have the least probability, and you had started from a large set, and you'll keep throwing it, keep repeating this till you come to the desired size that you wanted, because in every iteration you are throwing away some number of tokens. Is that okay? Now the question is to deal with this listing down all these segmentations for a given word, right? How do you avoid that, right? So you avoid that using a dynamic programming algorithm. So here's whereby, okay? So I start with W, okay? So I assume that I'm going to segment at W, okay? So I'm going to segment at W, then the probability of the token W is, or the log probability is minus 4.29. So segmenting at W. Now when I am at WH, there are two possibilities, that my segment is W comma H or it is just WH. So I have to compare these two paths. One path is W comma H and the other part is WH. How do I compare these two paths? I just take the probability of W multiplied by probability of H and the W probability of WH itself, right? And here we are dealing in log probabilities, so I'll just add this, right? So W plus H, adding the log probabilities, I get minus 7.63, and WH, the log probability is minus 5.99, right? So what does that mean? Up till point 2, my best segmentation is WH, right? So then I don't need to consider segments of the form WH, comma, whatever, right? This has been ruled out. Do you understand that? Right? So now I have eliminated a choice. So earlier I was listing all possible segmentations. In listing all possible segmentations, WH, comma, E, comma, R, comma, E would have been one segmentation. W, comma, H, comma, ER, comma, E would have been one segmentation. E, comma, RE would have been another segmentation, right? But now I have eliminated this early, that W, comma, H, that sequence I am not going to extend at all, because WH is a better choice than W, comma, H, right? So that's, you see how now you are going to prune, you are not going to enumerate all the possible options, right? So let's just continue with this and see where we end up. So you have decided that up to sequence length 2, or the first 2 characters, the best segmentation is WH. So now you just need to continue that. Now what will you do? So then the possibility is that, yeah, so WH is what you have selected. So now WH, I'll come back to this, right? So whatever I'm showing in red is only for illustration. You would actually not do that, right? I already said that you will not go for the tokenization WHE because you have already ruled it out. But I'm just continuing that calculation for illustration, right? But at this point, what is the choices you have? You have WH, so you could extend it and say WHE, or you could just consider the token WHE itself. Yes, right? This is the choice that you have. So let's see what that choice turns out to be. But turns out that WHE is not a token at all, right? It's not there in your vocabulary at all. So that option is not available to you, right? But it could also have been possible, yeah. So now again WH, comma, E is what the best tokenization you have at this point. Yeah, the other option would also have been W and then HE, right? So that, because W, comma, H sequence you are not continuing, but W, comma, something sequence is still not ruled out, right? So W, comma, HE you still need to compare, and between W, comma, HE, WH, comma, E and WHE, WH, comma, E is the best sequence, right? So now again the other sequences will get discarded. So you don't need to consider, you don't need to continue this sequence anymore, because up till character 2, up till character 3, you have found out that the best path is this. So any other path you don't need to extend, right? So you'll just continue in this manner, and you will not be enumerating all the possible sequences, because here again I repeat, W, comma, HE, comma, R, comma, E is a sequence possible. W, comma, HE, comma, RE is a sequence possible. But you have decided that you are not going to consider these sequences, because up to WHE, the best segmentation was just WH, comma, E. W, comma, HE was not a good segmentation compared to this. So you don't need to extend this, you just need to extend this one, right? So that's how it operates. It does not enumerate all those, but it keeps pruning the ones which are not required, right? So that's how the sentence piece tokenizer works. You start with a large vocabulary, right? You compute the probability of every token. Then for every word, you find out the best segmentation that it can give you, right? And then that segmentation will lead to some new tokens, because if you decide to segment it as SO, ME, TH, ING, so now these are the 4 tokens which are going to replace this word. So throughout the corpus, this is changing now, right? What are the tokens coming out of every word is changing. That means the probabilities of the tokens will change, because some would increase, some would decrease. So again you will compute the probabilities, throw away the ones which are lower, and then keep repeating it, right? And the only bad or the complex part here was enumerating all segments, which you are doing by a dynamic programming algorithm. So you are pruning it and it's operating very efficiently. You are not listing all the possibilities, okay? So that's all. So that's all about all the tokenizers that we wanted to cover. So quick summary, you have character based, you have word based. This is very small, this is very large. Small has the problem that your sequence lengths would be very large. Big has the problem that your softmax would be very large. So you wanted a middle point, which was subword tokenization, and there we looked at 3 methods: BPE, word piece, and sentence piece. BPE and word piece start with small and keep increasing till your budget. Sentence piece starts with big and keeps removing till your budget, right? And BPE and word piece were related in the sense everything was same, just word piece introduced this new scoring function which sort of prioritizes tokens which are more prominent then other options that you have at that point. Okay. So that's all about tokenization, tokenizers. We'll end this lecture here. Thank you. I'll see you in the next class. Okay. Thank you.